Hello, YouTube, and welcome. Today we're going to be talking about pendulums, which is sort of the second main case that can come up for simple harmonic motion. The third main case that can come up for simple harmonic motion is going to be part of our gravity extravaganza. That one is really weird and will almost definitely not come up, but it's like this super cool edge case, so like every physics class is like, oh, we gotta talk about this one because it's so weird. So that's a special treat for next one. For this one, the special treat is the example problem at the end is dumb and I love it. And so I don't normally say this, but I'm actually excited to talk about the example problem. Go figure. All right, so ideally, end of the day, you should be able to identify and model simple harmonic oscillators for pendulums. So same way as the last one in particular, it's basically doing all the same stuff, but instead of for a spring setup, we're going to be doing it for a pendulum setup. So taking a sec, talking about how it worked for springs. For a spring, your period was only dependent on the mass of the object, where bigger mass meant it took longer to finish, because at every point along the way it's harder to accelerate, and so it takes longer to accelerate it. And the spring constant, because at every point along the way it's getting a stronger force accelerating it, regardless of how far it's pulled back, for a set distance that it's pulled back, I should say. And so you wind up taking less time because you'll have an higher average velocity. When your x is at its maximum, your velocity is 0. When you're at that point as well, if it's a positive maximum for your displacement, your acceleration will be its negative maximum. When your x position is 0, your velocity is going to be either the positive or negative maximum, and your acceleration is going to be 0 as well. As will your force. Energies follow suit with those two things as well. You should hopefully be able to figure out the velocities using energy and displacement, and you should be able to figure out the accelerations and forces using force, and negative kx from a spring will equal mass times acceleration. Not on this list, you should also be able to think about things in terms of how many quarters of a period the person has gone through, which we'll get a little bit of practice with from this one. And you should also be able to, instead of using energies and displacements, using the first and second derivatives of your position as a function of time equation to figure out what velocities are going to be at a given point in time, or what accelerations are going to be at a given point in time. So, pendulums. Moving on. A lot of the stuff from the pendulums is going to be really similar. The geometry is going to be miserable. Something also worth noting here is that this only works for pendulums with a small angle, but it will work for physical pendulums, which are basically pendulums where you have a non-zero mass for the string. The only difference for a physical pendulum should be that you have to use the moment of inertia instead of using the mass to determine how the object is going to move. Well, without further ado, let's swap to paper. So we've got a pendulum. For our pendulum, we're going to say that it starts at a position that is all the way over on one side. And when it does that, it'll be at some angle away from its rest position, which we will call theta max. It'll then swing down to the bottom, and it'll then swing up to the left, and then back down to the bottom, and so on and so forth, back and forth. When it's up at the left, it'll be at an angle of negative theta max. So if we're looking at this, in a lot of ways, this is going to function very similarly to the spring. You're taking some potential energy, you're converting it into kinetic, then back into potential, then back into kinetic, then back into potential, and you're sort of going back and forth between this motion where you're off of the middle. gravity is going to be pulling this object, some component of gravity is going to be pulling this object radially, and some component of gravity is going to be pulling this object tangentially. The component of gravity that's pulling this object tangentially is going to be pulling it back towards the center. Meanwhile, if we're on the other side, we'll get the same thing where it's getting pulled back towards the center this way. Yes. Let's go through a similar process where once again we're going to start thinking about what the forces on it are. We're going to start thinking about what that has to do with the acceleration and go from there. Well, the forces that are on this object will need to be equal to the mass times the acceleration tangentially, if we do the tangential forces. Well, the net tangential force on the object, if we do a free body diagram, we're going to have the force of tension going this way. We're going to have gravity going straight down. Some component of gravity will be going tangentially. Some component of gravity will be going radially. The tangential component of gravity, if we look at the geometry of the situation, this is our rope. This angle will need to be the same as this angle. So if I redraw it on the other side, it'll be a little easier to see. Our tangential component of gravity, this one, will be mg times the sine of our angle. So what I can now do is say that my tangential force is going to be mg sine theta, and that will need to be equal to mass times our acceleration tangentially. The problem is twofold. First off, we've got this random sine function hanging around. So we don't have what we had with the springs, where we have acceleration is equal to something related to x position or tangential location. Pooh. Well, let's try thinking about it a slightly different way. If we look at this object, our tangential acceleration, using what we know from the rotation unit, will need to equal our angular acceleration times the radius of the circle for our pendulum. Well, the radius for the circle of our pendulum is our length. So alpha times L. If I go ahead and plug that in, mass drops, we'll get g times the sine of theta is equal to our acceleration times the length of our pendulum. Something that I have to be a little bit careful about here. This force, when we're on the right, is going to be trying to get our object to spin, is going to be out of the page for the torque that it generates. Whereas if we're, sorry about that, my camera glitched out for a sec. Whereas if we're on the other side, our object is going to be such that it will be going down into the page. So when our angle is a positive angle, we'll get a force that's negative. So I actually need to throw a negative sign here to accurately catch the direction of the force. Okay, now we get to the tricky part, because we don't have the right equation form still. What we've got instead, divided by L, is negative g over L, which will be a constant, times the sine of our angle is equal to the second time derivative of our angle, because angular acceleration is the second time derivative of angle. Bummer. This isn't quite right either. This is where the small angle approximation comes in, and this is part of the probably the weirdest part of this. For small angles, if you look at a graph of sine theta, it looks like this, right? If you zoom in just on this section here, it looks a lot like this, which looks a lot like a line. And if you graph it in radians, it looks a lot like a line with a slope of 1. So specifically, if your angle's below about 15 degrees for your maximum angle, your object will be such that your sine of theta is basically the same thing as theta in radians, and it has to be in radians. If it's in degrees, it just does not work at all, because the sine of 15, like, there's no way that the sine of 15 would be 15. That just, sine can't be bigger than 1. But for radians, when you're going up to about pi over 6, pi over 12, then for around up to about pi over 12, you'll get decent numbers for this. So what that means is that our sine of theta is going to be really close to being equal to just theta. So now what we can say is that negative g over L times theta is basically the same thing as the second time derivative of theta. And so now, just like we had before for our equation set up for our springs, we're going to have the same equation set up for the pendulum using theta instead of using x. And so what that tells us is that this constant that came out at the front, this is once again going to be equal to the stuff inside the trig function, which I'm actually going to call k for this one so that I don't confuse it with the omega that's going to wind up showing up in the equations, squared. And this is coming from our theta max times our cosine of theta times our omega, or sorry, our k, that's why I'm not using omega, times our time will need to equal our theta. If we take the derivative of that, we'll get negative omega max times k, times the sine of kt is our angular velocity. And with our second derivative, negative theta max times k squared times cosine of k will need to equal our alpha, or our second derivative. So our original function was theta max times cosine, and so what we're left with is k squared is the thing that's floating out in front of our original function. So whatever's floating out in front of our original function, in this case g over L, will need to equal the stuff inside our trig function squared. Doing that out, g over L square rooted will equal the stuff inside our trig function. So once again, using that, and I'm going quickly here because I went slower and in more detail on the other one, and the process is very, very, very similar. It's just swapping out the angular variables instead of the linear ones. Will be such that if we want to figure out the angle that's being swept out by this pendulum, or how far it's moved to one side or the other, we can do that by saying that our angle is going to be equal to the maximum angle times the cosine of the square root of g over L times our time. And our omega is going to be equal to the negative theta max times root g over L times the sine of root g over L times our time. And our acceleration is going to be equal to negative theta max times g over L times the cosine of root g over L times our time. Great, that's our setup. From there, we're also going to need to get our period, just like we did for the last one. Well, just like we did for the last one. When the stuff inside here is equal to 2 pi, the time will be the amount of time it takes to complete a full cycle, because sine and cosine complete a full cycle every time that the inside equals 2 pi. When root g over L times our period is equal to 2 pi, we're good to go. Multiply each side by L over g square rooted, multiply each side by L over g square rooted, and we'll get that our period is equal to 2 pi times the square root of L over g. What's interesting to me about this one is that with the last one the mass mattered, with this one it doesn't. Because we get more force when we have more mass, just like how we got more force when we had more angular displacement. The other thing that's weird to me about this one is that even though gravity is the force that's accelerating it, the further back we bring it doesn't change how long it takes. Because the further back we bring it, again, increases how far we have to go, and again, it actually increases the amount of forces pulling it towards the center. Because it's not just gravity that's doing it, it's specifically the part of gravity that points towards the middle. And when your theta is bigger, the part of gravity that points towards the middle is also bigger, just via the geometry of the thing. So, the thing that does matter, though, is that if you increase the length, and you can see this by just sort of drawing two lines at the same angle originally. Going from here to here versus going from here to here, the distance gets bigger in the second case, even though the angle stays the same. So the amount of force that we have stays the same when the length is bigger for a set angle. But the amount of distance that we have to travel is increasing. So more distance, but the same force, means that you wind up taking more time to do it. The only way that you can make the period of the pendulum be shorter than by making something else bigger, I should specify, you can make the string shorter and that would make the period shorter, is by changing gravity. If you have a planet with stronger gravity, then because at every step along the way it's getting accelerated more, it takes less time to finish. Yep. And that's the period relationship. So we've got our old equations, they still work. Yeah. Something that's a little bit relevant here, more so than it was for springs. A lot of the times for this one, if you're trying to figure out a velocity, you're really just going to be using the energy for it. And a lot of times, if you're figuring out the acceleration, you're just going to be using the force, because getting it back and forth between angular and linear is kind of annoying. Like, it's not too bad. You can just multiply each side by L, because angular times L will get you linear. And when you do that, you'll mostly just be swapping out the x for the theta for x and the theta max for x max. But in particular for x, it's not going to be x. It's going to be arc length, which is super weird. For velocity, it's not that bad because it's going to be tangential velocity, and for acceleration, it's not going to be that bad. It's going to be tangential acceleration, but it's going to be super weird for your position equation in particular, which is why we're using the angular ones for this one, and why the equations work better with the angular ones instead of the linear ones. All right, so our main takeaways from that. The period of your pendulum is only going to depend on the length of the pendulum, in which case it's directly proportional to the square root of it, and the gravitational constant, inversely proportional to the square root of it. When your theta is at a maximum, your velocity and your angular velocity are going to be 0, and your angular acceleration is going to be at its negative maximum, as is your tangential acceleration. When theta is 0, on the other hand, your velocity is going to be at its positive or negative maximum, and your acceleration is going to be 0. When theta is 0, that's specifically when your object is in the center of the thing. So you can again figure out velocities using energy and displacement. You can again figure out acceleration using forces, but for this one, you're going to be using forces where negative mg sine theta, or typically, because of the small angle approximation, because otherwise this whole thing doesn't work, mg theta is about equal to ma, and then you can get the masses to drop. On to our example. A stunt driver rides a motorcycle at 20 meters per second off a ramp at a 30-degree angle. At the highest point in their jump, they grab onto a 20-meter long rope hanging from a helicopter. What is their maximum height above the point they grab the rope? How long will it be from when they leave the jump to when they reach this point? And then we need to describe how they'll move if they let go at their maximum height above where they grab the rope. So a lot going on here, and the physics of it, more so than the image of it, although the image of it is rad, is really weird. Or I don't know. I think there's a couple twists and turns as we go. So starting off, we've got this jump. It's at a 30-degree angle, and we've got our person driving off. They've got an initial velocity of 20 meters per second. Immediately I'm seeing this, I'm thinking components. I can feel it, you know? Then we've got the situation where they go up, they get to here, and they swing up to some maximum height. So I'm going to call this one H2. I'm going to call this one H1. H1 happens at their earlier max height. And then for A, we're asked for what H2 is. For B, we're asked for time 1 plus time 2, the time for the first section and the time for the second section, up to the max. And for C, we're asked for dropping and what'll happen when they drop from there or let go from there. So let's just start chaining together ideas. I said that I see an angle and I see a velocity and I'm instantly going to want to try to break it up into components. Let's just do it and then figure out if that'll be useful. Well, doing it, we've got 30 degrees. If we break it up into components, we'll get our velocity at our first location. We'll get v1 times the cosine of theta and v1 times the sine of theta. This is our Vx for the first distance. That's ringing some bells for me because that's pretty significant. specifically because our x velocity throughout the flight will be equal to our velocity at our maximum height, because there's no more y velocity at our maximum height and there's no forces on it in the x direction, so those are remaining constant. Great. So this is our velocity at this location. Can I do anything with that? Specifically v1 cosine theta. Well, they're going to grab the rope and then swing up to a second location. The kinetic energy that they have at their first location will need to equal the potential energy they have at their maximum height, because their maximum height is their maximum height, because they stop going any higher up. All right. So what that'll look like here is v1/2 v mass times the velocity squared at this, what do we even call this? I guess 1, 2, 3. V2 will need to equal mgh2, the height that they go for that second location. But I know that that's going to be equal to v1 times the cosine of theta. Mass drops. 1/2 v1 cosine theta squared, distributing that out, is going to equal to gh2. So if I want to find h2, I just have to divide each side by g. Neat. Well, we've got 1/2 times 20 times the cosine of 30. Oh, I got so close to making this problem useful. Squared, divided by 10. Well, that'll be 20 times the cosine of 30 squared. The cosine of 30 is going to be root 3 over 2. So root 3 over 2 squared is going to be 3 over 4, which is 15 meters. No, that makes sense. Yeah, this person will wind up going, yeah. So that's their final height. If we then start thinking about B is going to be such that we need to figure out the time it takes them to get from the bottom to the middle, and then the time it takes them to get from the middle to the top. Let's start with the bottom to the middle, because that's an older view problem and probably a good place to do, a good thing to do. Well, the time it takes them to reach their highest point is only going to be related to the y location, because the y location is going to be their highest point. Well, let's start with what information we know. We know that their acceleration in the y direction is going to be g, but down. We know that their initial velocity in the y direction is going to be v1 times the sine of theta, because it's just going to be vy. We know that their final y velocity at the top is going to be equal to 0, because that's why it's their maximum height. And so if we're looking for time, we can use this equation to get time 1 using acceleration, initial final velocity, and time. Final velocity is equal to initial velocity plus acceleration times time. That'll get us time 1. Great. I'm going to hold off on that until I have a strategy for time 2. For time 2, I'm going from the middle of a simple harmonic oscillator up to the top of a simple harmonic oscillator. So if I'm doing that, my period is going to be the time for the whole thing, and that'll be 2 pi times the square root of L over G. But I don't want the whole period, because they're not going from the middle to the top to the middle to the back to the middle again. I just want 1/4 of that, because I only want 1/4 of what happens from the middle to the top. So if I take this and I divide it by 4, that will equal time 2. So setting up our stuff for time 1. Our final is 0. So if I subtract off vy0 from both sides minus vy0 from both sides, we'll get negative vy0 equals at, divide by a, divided by a, t1. And we'll get that negative v y naught over a will need to equal t1, which will be equal to negative 20 sine 30 divided by 10, which is negative 10, sorry, which is 10 over 10, which is 1. So 1 second to get from the middle up to the top. For our next portion, period is going to be equal to 2 pi root L, which is 20, over G, which is 10. And all of that is over 4. So we'll get pi root 2 over 2, which is certainly a number. Relevant, it should be bigger than 1, because root 2 is bigger than 1 and pi is bigger than 2. So we've got about 3 over 2 times a number that's around, I think 1.4. So the time for the rope is bigger than the time while they're not on the rope, which makes sense for a number of reasons. The rope is pulling them up while gravity's pulling them down, so you don't have quite as much downward acceleration because the rope is canceling out some of that. And that's sort of one way to conceptualize it. The other big one is that they actually go a lot higher on the rope than they do off the rope. If they're in the air for only 1 second, they only reach a height of 5 meters before they stop. They only reach a height of 5 meters above the ground. So they make a total journey of 20 meters up in the air, which is insane. Small angle approximation actually won't work for this one at all. Oops. But your setup will be such that they go way higher and way longer on the rope than they do off the rope. So taking those two and putting them together for time 1 and time 2, what we'll wind up with is that our total time will be equal to 1 plus pi root 2 over 2 seconds. For C, this is sort of the last little thing that I think is kind of neat about this one. Their velocity is 0 at 0.3. So if they let go, they'll just fall straight down. They're not moving sideways. So they drop straight down. If you're ever swinging on a rope and you need to move sideways, it's actually really important that you don't wait for the rope to swing out as far as possible before letting go, because you won't be moving sideways at all when that happens. Now, if the fall is really, really short, in theory, that could maybe get you further, but most of the time, if there's a significant fall afterwards, so for example, if you're going off like a rope swing off a cliff or something, which happens sometimes, you actually want to let go when you're not at the top yet, because you want to launch yourself somewhat sideways and somewhat up, so you can maximize your time in the air as well as maximizing the distance you travel sideways during that time in the air. You can run into a lot of problems if you're letting go right when you reach the top, or if you're letting go on your way back down, because on your way back down you'll actually have a negative x velocity and get pushed back towards, well, not pushed back towards the cliff, travel back towards the cliff as you go. So, that's pendulums. That's all the stuff you can do with them, sort of. But at least it's a good starting point. Goodbye, YouTube.